Swayam Prabha. Digital India. Educated India.
Dear students, today we are starting with another lecture on the lecture series related to the course material on Transportation Engineering 2. In today's lecture, we will be looking at the aspects of speeds on track. This is in continuation of the geometric standards which we have discussed in the previous lecture, where we discussed about the curves and the super elevation and provision of super elevation and its design. Before that, we have already discussed about the fixing of an alignment and the factors needs to be taken or considered while fixing any alignment of a railway track. In today's lecture, we are going to take the speed and its effects, the safe speed, the equilibrium speed and maximum permissible speed. And finally, we will try to look at the computation of speed with respect to the given cant or the computed cant or the super elevation. Now, we start with the speed. The very first thing is that there are different ways in which the speed can be defined. As we understand, the speed is the rate at which we are covering any distance. Now, in this case, it may be defined in the way like it may be the average speed or the maximum speed. In the case of the tracks or maybe in any of the cases of the transportation systems we take in general, we find that the speeds have been defined in different forms for the design purposes. Here in this case, we are talking about that every train is allowed to move on track with two defined speeds, namely average speed and maximum speed depending upon its category. So, as we know that there are different trains which are running on the tracks, and all these trains have been defined or categorized on the basis of their speed characteristics, mainly that is they have been defined to move at certain maximum speeds, and with respect to those maximum speeds the average speeds are also defined. Average speed is the speed which is helpful in defining or in finding out the total time period a train is going to take so as to cover a distance, whereas maximum speed is the value which a driver is allowed to attain subjective. There is a requirement of attaining that value. At the same time, there are certain sections in which they are allowed to attain this higher value so as to economize on the travel time. So, we have to look at both the factors, that is how we compute an average speed or how we are computing the maximum speed. Now, when we talk about the maximum speed, we can go to any limits, as in one of the previous lectures I have told you that the maximum limits can go even up to a value of 500 to 550 kilometers per hour. Even in our Indian Railways condition, now we are aiming at achieving the higher speed of some around 250 kilometers per hour, and some corridors have been identified which are going to be transformed into the high speed corridors, where the trains will be moving at a speed of 250 kilometers per hour. So, how we are going to fix up that speed and whether it is related to any safety measure to be taken up, so that there is no accident taking place or the hazardous conditions are not getting created. In that sense, we have to look at along with the maximum speed on the safer speed too. So, it means there will be different categories of speeds which needs to be understood and which needs to be examined or computed. Now, we will look at the different things. The average speed depends upon the length of the section and the number of stoppages. Even if we are providing the maximum speed, and the maximum speed can be attained by a train between two stations, then that is going to economize only on the distance which is being provided between those two stations. But in the case, as we have seen while fixing an alignment, the alignment covers number of places so that the revenue can be generated. In that sense, there will be two terminal stations, the station from where the train is starting and the station at which the train is finally ending, and in between it will be passing through number of other stations. Therefore, there will be on all these stations the train has to stop down. So, it means it is losing some time while stopping, it is also losing some time while deaccelerating, and it is also losing some time while accelerating. If the train is allowed to move on a constant speed from point A to point B while it is passing through point C, D and E, then there is not going to be any loss, but then in that case there cannot be any stoppage. Therefore, whatever are the number of stoppages and whatever are the lengths of the sections, because this is another thing, if the length of the section is small between the two stations, then the maximum speed cannot be attained. As soon as the train starts attaining the speed, probably the time comes after which it has to deaccelerate so that it can stop at any other station. So, that is a condition which is generally found in the case of urban railways, where like in the cities the trains have been provided. If we talk about those things, then we have metro in Delhi, or we have suburban rail system in Mumbai, or another metro in the Kolkata, and likewise ring railways in Chennai. So many categories are there where the length of the section also matters, because the train is not being allowed to attain the maximum speed at that section, as the length of the section is very less. So, this is one thing which is related to the average speed. So, therefore, what we have to take is that we have to find out the total time period which it has taken from the station A to station B via station C, D and E, and the total distance which is there between point A and B. So, the distance divided by the total time will give us the average speed, and obviously now it will be covering that amount which it has spent or in stopping or in accelerating or while the train has been stopped at any of the station. So, for every track there is another thing, that is maximum sanctioned speed, and this maximum sanctioned speed is defined by the track engineer who has designed that section. So, there are number of factors on the basis of which this maximum sanctioned speed can be defined, and there are of course Indian railways as well as the other railways in the world have devised the formula so as to find out this value of maximum sanctioned speed. So, this is another value. Any train which is moving on any of the section is not allowed to cross this value, because this is the most highest value which is being allowed by the track engineer, and this value is the last value which is being taken into consideration while designing that track. If we overcome or we come out of this particular value and it is being exceeded, then are all chances that any accident may take place. So, as to remove those hazardous conditions, it is better to be far below this maximum sanctioned speed. But in the case of emergencies, with the permission of the competent authorities, these maximum sanctioned speeds can be attained by the drivers of any train. So, this speed limit can be used during the time of emergencies with prior permission of authorities. That is what I have already enumerated. Now, in the case of speeds, we have already seen that the speed creates its effect in the augmentation of stresses as well as in the augmentation of the resistances. There are number of things in which the speed plays its role. There may be curvature, there may be a gradient effect. In those cases also at times the speed has its effect. So, we will be looking at some of the dynamic effects of speed now in this lecture at this point of time. So, different effects are like pitching. In the case of pitching, what happens is that there is a sort of a throw in the forward direction or in the side direction. That sort of a throw which is coming because of the irregularities of the surfaces, or maybe because of the poor maintenance of the joints, whatever are the reason, this is one of the effect which may be there, and the passengers who are sitting inside the wagons, they may feel that there is a throw to them in the forward direction, or they are feeling a throw towards the side, or so hitting towards the side of the bogie. So, this is one type of effect, and obviously as the speed increases, this tendency of getting a pitching may also increase. Another effect is rolling. Rolling is a effect where there is a movement with respect to the x axis. In the case of x axis, like that is the longitudinal movement which is taking place along the track. If it starts just moving in the clockwise or anti-clockwise direction of that axis, then that is termed as rolling. But in the case of the trains, it is not taking a complete turn like this, but then there is a leaning effect towards the left side or towards the right side of the direction of movement, and that can be termed as a rolling effect which can be there. And you will found that generally it is happening in the cases where like the curves have been provided or the sections have been provided where there is a difference in the outer and inner rail levels. In such conditions, there are tendency of the material as well as of the passengers moving towards one side, and that is the rolling effect which comes in. Then the next effect is bouncing. Bouncing is a condition where the train has a bumping effect at the same location where it is. Whereas in the case of pitching, it was a forward or the backward condition throw. In the case of the bouncing, this is in the vertical direction. So, the train has a vertical movement, and with that vertical movement, like you feel a jerk in the upward direction, or you feel a sort of a deflection in the downward direction. So, that is a effect of bouncing, and bouncing effect may be coming again because of the irregularities in the track, and as the speed increases, this effect of irregularity increases tremendously. Or maybe it is a condition which may be observed at that point where there is a joint, and due to the impact or the difference in levels of the two rails, a bouncing effect may be coming. Then this is one aspect which we have been discussing from the very beginning, is that there are all chances of lateral oscillations or sways taking place on any rail section. And probably, if I understand that you must have observed this whenever you have traveled by train, that the train moves in either of the directions, which is in the lateral direction when it is moving in any forward direction. So, that is a lateral oscillation which keeps on coming, and as soon as it hits on the one side, it rebounds back and moves towards the other side. So, you feel that your compartment is moving sideways, and that is a relative motion of the compartment in the sideways with respect to the another wagon or the compartment. That is what is a lateral oscillation, and this effect of lateral oscillation increases as the speed increases. This is another effect of the speed, and we will found that if the speed is very heavy, then these oscillations may be so heavy that there are chances of overriding the rails. That becomes obviously the hazardous condition. Then there is a resonance. Resonance is must have studied in physics, that it is a condition where the frequencies of the two systems starts matching. Now, when this is happening, here we are talking about the two metal surfaces. One metal surface is in the form of a rail, and another metal surface is in the form of the wheels. So, when these two things are interacting with each other, there is a continuous smooth movement on this one, and at the same time there are chances where there are impacts or bouncing effects or pitching effects, as we have discussed just above. Then the frequency of the two may match, and as soon as there is this frequency matching is there, the sort of vibrations will start moving in to the persons or to the freight which is being transported. So, this is another condition which at times people have observed, that they feel a sort of a pinching effect which is coming from the bottom while they are sitting on any seat. So, that is coming because of the resonance which has been achieved at the bottom at the track level. Then springing action is coming out from due to the reasons of the springs being provided at the bottom of any wagon so as to take care of the movements in the vertical direction. So, if this springing action may be there, again unless and until it is a very smooth track where the levels have been maintained, where the gauge has been maintained or the alignment has been maintained properly, the joints are perfect, then you are not going to observe this springing action. But otherwise, if it is not there, any of the problems are there, you will observe that you are having oscillating condition in the vertical direction. So, you are going up and coming down and going up and coming down, that is what is an springing action which will be there. And this springing action is controlled by the devices which tries to dampen out these type of effects, and you will find that if we move from the normal category of wagons to the higher category of wagons, then this springing action reduces by a large amount. So, that is because a better springing devices have been provided and those higher category of wagons as compared to those other lower category of wagons. And then the suspension characteristics are there. Suspension characteristics again they are related back to the springing action. We can say is that it is trying to having a suspended condition along the wheel bases, along the axle bases which have been provided, because they are the number of bogies which are provided so as to make a compartment, as we have seen in the case of locomotives too, that when we define them by any nomenclature or by define them by the number of axles or the number of wheels, then it is not that the whole of those wheels have been provided on the same bogie. There are chances that there are 2 or 3 bogies which have been provided at the bottom. So, when that is being done, then there is a suspension effect which remains between those bogies. So, there are other characteristics which get enhanced because of the speed. So, these are some of the problems or some of the effects which are caused because of speed. Now, we come to the important point, that is how to compute the safe speed, because all the trains which are allowed to move on any of the track, they should move with a speed which is lesser than the safer speed, or at the maximum they can attain this speed. And after this one, then we have a maximum permissible speed or the maximum sanctioned speed of the track, which obviously can be taken up when there is an emergency. So, the safe speed on the straight track, in this case it is limited by the maximum speed defined for every train. As we know that there are different categories of trains. We have passenger trains, we have express trains, we have super fast trains, and then we have the other categories like Rajdhanis and Shatabdis. So, all the categories of these trains, they are having their different values as maximum speed. So, they have been defined by the categories. So, this safe speed is also going to be governed by the similar thing, that is the maximum speed defined for every train. So, it has to be less than this, or at the maximum it can attain this value of maximum speed. Then vehicle characteristics differ within different categories of train. This is the reason why this value is going to change, because the different suspension systems or the safety features or the springing actions, everything, they are all different depending on the type of the category of the train, and that is for what the railways charges you when you travel by that particular category of train. So, when these characteristics are changing, then obviously in that case the speeds can also change, or we can go for higher speeds if better characteristics have been provided. In the case of the curves, it is going to depend on certain factors, like it is depends on the gauge, that whether we are providing a broad gauge or a meter gauge or a narrow gauge, the radius of the curve, it is also, you can see that it is the degree of the curve or the radius of the curve, it is going to depend on that one. If the radius of the curve is bigger or large, then obviously it is a flat curve, and negotiating a flat curve with a higher speed is not a problem, but when the curve is quite sharper, then the higher speeds cannot be attained. Then the value of super elevation, this value of super elevation is another thing, because this super elevation, as we have seen in the previous lecture is nothing but is GV square divided by 127 R. So, it means the super elevation and speed, they are correlated. Super elevation is correlated with the, it is proportional to the square of the speed. So, that is how if we are providing certain value of super elevation, then we can find out the related speed or the restricted speed, and this is what we have seen previously too, when we have computed the values in the case of negative super elevation being provided on a branch line with respect to a main line. Then transition curve length is another case. Here it is governed by the length of the transition curve, and this transition curve provides the smooth entry of the train from the straight section to the curved section, and if we cannot provide the complete length of the transition curve, then the value of the safe speed needs to be restricted. But in case there is no problem in providing the overall length of the transition curve, then whatever value is being found out by the different other methods, then that can be provided on the basis of that one. Then resultant of weight and centrifugal force, this is another aspect which we have discussed when we devised the formula of super elevation, that is E is equals to GV square divided by 127 R, where in that diagram we have seen that the vertical weight is acting vertically downwards and the centrifugal force acts in the horizontal direction, and their resultant acts at an angle alpha with respect to weight in the horizontal in the downward direction, and this falls within the two wheels which have been provided on the axle. So, this is another thing, means we have to see that the resultant is not falling away or out of that wheelbase, otherwise it will create the overturning moment condition. So, now we look at how we can compute the safe speed. There is a Martin's formula so as to compute the safe speed. This is quite an old formula and it depends on the radius of the curve, which is taken in meters. The speed for transition curves like the broad gauge curves or the meter gauge curves, in that category this safe speed Vs is given by 4.35 and under root of the whole value of R minus 67, and this comes in kilometers per hour. So, this is one formula in the case the transition curves are provided on that track, and this is for the broad gauge and meter gauge condition, whereas or it can also be simplified as 4.4 and under root of R minus 70 again as kilometers per hour. Then in the case of the narrow gauge, and again the curve is being provided with the transition curve, then Vs or the safe speed is computed by 3.65 under root of value of R minus 6 again in kilometers per hour, and this is subjected to a maximum value of 50 kilometers per hour. So, whatever value we are getting using this formula with respect to the radius of the curve, if it is coming more than 50 kilometers per hour, then this is the maximum value which can be allowed as a safe speed on the track. Then in the case of non-transition curves, the speed can be computed as 4 by 5 of the above all cases. Whatever value we have computed in the case of transition curves, if we take 4/5 of that value, then that is taken for the non-transition curves. And in this case for the narrow gauge, it is subjected to a maximum value as 40 kilometers per hour. Then there is another formula which is given by Martin for high speed conditions or high speed tracks, and here the safe speed can be computed as 4.58 under root R. So, this is a simpler formula so as to find out the speed on the high speed tracks. But in the case of Indian Railways, no longer we are using the above formula of a safe speed on curves. What we are using is now being defined as safe permissible speed instead of simply the safe speed, and this safe permissible speed is computed by a formula which is given by the railway board, and this formula replaces the Martin's formula. This formula considers the cant actually provided on the track, that is the super elevation which is being provided on the track, and the standard deficiency allowed in it, and the value by which any deficiency is being allowed in the value of the super elevation being provided, that is whatever is the amount which can be provided as the maximum or whatever is the amount which can be provided as a minimum. Considering those values, then we can find out the speed, and this is allowed in it along with the radius of the circular curve. So, it means it is trying to consider three things. One is the super elevation, one is the deficiency in terms of the cant deficiency or cant axis or the radius of the curve. So, these three values will be there. Now, we look at how we are computing this value, what are the formula being given by the railway board. In the case of fully transition curve, it says that it can be computed by V equals to 0.27 and under root of the whole value of R multiplied with CA plus CD, where CA is the actual super elevation or cant being provided on the track, and CD is the cant deficiency which is allowed on that track. And this is a case for a meter for a broad gauge, and in the case of meter gauge, the formula is 0.347 under root of the whole value of R multiplied with CA plus CD. So, the formula are more or less similar. The only thing is that the value of CD will be changing with respect to the broad gauge or the meter gauge. CA remains the actual super elevation which is being provided, and this factor is changing here from 0.27 to 0.347. In the case of narrow gauge, the value remains as the same formula as being given by the Martin, that is 3.65 under root of the whole value of R minus 6, and it is subjected to a maximum value of 50 kilometers per hour. In the case of non-transition curve, the values needs to be found out based on the cant to be gained over virtual transition, which is 14.6 meter on broad gauge, 13.7 meter on meter gauge and 10.3 meters on narrow gauge. So, this is the way how we compute in the case of non-transition curves where the super elevation has been provided. Now, we come to the non-transition curve conditions where in this case again if the super elevation has been provided, that the cant gradient that should not exceed 1 in 360 on broad gauge, whereas in the case of meter gauge and narrow gauge it should not increase above 1 in 720. So, on the basis of this value of 1 in 360 or 1 in 720, that is the rate at which the super elevation is being provided, and that is one of the criteria of finding out the length of the transition curve. So, we have to, because there is a restriction that the transition curve has not been provided, then using this value we can compute the distance by which the super elevation can be attained. Further, when there is no super elevation being provided in the case of a non-transition curve, that is no transition curve is available on this track, then we calculate the maximum cant deficiency to be gained or lost, and for in that case we use the rate of change of cant deficiency, and the value is taken as 35 mm per second for broad gauge and 55 mm per second for meter gauge. These are the standards or the IRS standards related to the cant deficiency, change in cant deficiency. Further, when there are curves with the inadequate transition, then in that case the actual cant or cant deficiency with consideration to its limiting value, that becomes the criteria for finding out of or calculating the VM. We take the actual cant which is being provided, and we are considering the cant deficiency up to its limiting values. Then considering rate of change of cant or cant deficiency within their limits, we try to find out the permissible limits of speed. Now, once we have idea of this permissible safe speed or safe permissible speed, the next thing comes into consideration is the equilibrium speed. This is the basis of the design of super elevation, and this is defined as the speed at which the effect of centrifugal force is exactly balanced by the cant provided. So, that is what we have been talking when we have discussed the cant, then we have found that there are certain problems with respect to the centrifugal force. and in that case what was happening, there was unbalanced condition of the load or the forces which are acting on the inner and the outer rail. So, as soon as the super elevation is being provided, it just counteracts the effect of the centrifugal force. Now, when this counteracting is being achieved and now we have the same resistance on the two rail sections provide side by side, that at that point of a time whatever speed can be attained, that speed is the equilibrium speed. And this is decided based on a number of factors. It is decided using the maximum permissible speed Vm on that track, which is generally decided by the track engineer who has designed this track. Then there is a permanent and temporary speed restrictions which are employed on the track for the movement of different trains or the rolling stock, and this restrictions they come by the traffic controller who is controlling the traffic on all the track or on the track which comes under one division or a junction from where a big section has been controlled. So, the person who is controlling the overall traffic, the trains which are moving on different tracks in different directions, the person is known as traffic controller. That is the one person who controls all these things, and that person can impose the speed restrictions depending on actual conditions. Sometimes these may be temporary, sometimes they have to be made permanent depending on the problems associated with the track. Then the other thing is the number of stoppages. As the number of stoppages increases, as we have seen or discussed previously, the speed is going to reduce. But then it is to be done with respect to the revenue requirements or the generation of revenue for the railways. Another aspect is gradients. The gradients we have discussed previously too. If there is a grade resistance, then it has its effect on the reduction in the speed. And here when you are talking about the equilibrium speed, then the gradient should be such that there is no reduction in the speed, then that particular gradient is to be taken into consideration. Now, the next point in the case of the equilibrium of speeds is the proportion of slow and the fast trains. Not all the trains are moving with the same speed on any track. So, in that case we have to look at what are the total number of trains moving in any of the speed category, and based on that then we can compute the value of the equilibrium speed. So, we will be looking at how we can find out these values in the further slides. Now, this equilibrium speed or we can calculate here it is being designated as V E. In the case of the conditions where the maximum speed is greater than 50 kilometers per hour, that is in the most of the cases where we are talking about above narrow gauge, then in this is V E is taken as 3/4 of Vm or Vs or whichever is less, where Vs is the safe speed or safe permissible speed being defined for that track, and Vm again is the maximum permissible speed which is allowed. We take the 3/4 of that or Vs, and then whatever is less is computed taken as the equilibrium speed. In case the Vm is less than 50 kilometers per hour, then we will be taking Ve as either Vm or Vs or whichever is less. So, this is another way of finding out this value. Further, we have the weighted average, where we are talking about a condition like it is computed as Ve is equals to N1 into V1 plus N2 into V2 plus so on, and this whole is divided by the value N1 plus N2 plus so on, that is the summation of the numbers. So, here what is happening is that we categorize the trains by their speed bands, and then for the mid block condition of that speed, that is V1, we find out how many trains are moving in this speed band, that is N1. So, if we have this categorization as different speed ranges are there starting from 1 to m, then we have the mid block condition of that speed range as V1, V2 up to Vm, and for each of that category we will be having N1, N2 to Nm. So, now we have number of vehicles here, and this is the multiplication of number of vehicles in that category of speed band with the speed. So, we get that weighted average, and this is how the equilibrium speed can also be computed This is the condition where we are taking into consideration the number of trains which are moving at a slower speed or the trains which are moving at a high speed. Now, we come to the another point, that is maximum permissible speed. This maximum permissible speed on a curve is the minimum of the values calculated as. Here we are talking about, we are assuming that the length of the transition curve, whatever it is required, can be provided, and therefore, there is no problem as such in this case. So, in that condition, the maximum permissible speed is computed as a minimum value of certain conditions, like the maximum sanctioned speed of the section. We have seen the sanctioned speed of the section by the track engineer. So, once we have got this value, then this is one criteria of finding the maximum permissible speed, and this is authorized by the Commissioner of the Railway Safety. Then the speed based on the consideration of Kant deficiency, we have to compute this value based on the Kant deficiency. As we have seen, there is a formula of finding out the speed as 0.27 multiplied with under root of R multiplied with CA plus CD, where CD is the Kant deficiency. So, if we use this formula so as to find out the value, then we can find out one more criteria, that is this one, and compare it with respect to the maximum sanctioned speed. So, these are the mainly two values by using which we can find out the maximum permissible speed. Now, further, the speed based on the consideration of Kant deficiency may be done in the form, like first of all we have to find out the equilibrium speed. So, what is the equilibrium speed is decided. Then once it is being decided, with respect to this equilibrium speed, the equilibrium super elevation is calculated. So, based on the raw data, based on the information collected from the track, that there are so many trains running with such type of speed, we have already calculated the equilibrium speed, and then we put it in the formula G V square divided by 127 R, we will get equilibrium super elevation E. Now, once this equilibrium super elevation is calculated, then it is added to the Kant deficiency, and this Kant deficiency, as we have seen previously tour, we are looking at the certain permissible values of the Kant deficiency for different tracks, and that value is to be added based on the type of the track to the value calculated in the previous step. So, we have the value now as CA plus CD, and for this value of CA plus CD, we compute the value of speed. So, that value is going to define the maximum permissible speed. Now, this maximum speed, taking into consideration speed of goods train and Kant axis, this is another criteria, because in the previous case what we have taken is that there is a equilibrium Kant. Now, when we talk about this equilibrium Kant condition and Kant axis and Kant deficiency, we have two conditions. The Kant deficiency is related with respect to the trains which are moving at a speed higher than the equilibrium speed. Now, suppose we are talking about the equilibrium speed as 80 kilometers per hour, and there is another train which is moving at a speed of say 120 kilometers per hour. Now, for the 80 kilometers per hour, we will be providing some super elevation, and that super elevation we termed as equilibrium super elevation. Now, if you take the effect of the centrifugal force which is governed by the speed, then for the value of 120 kilometers per hour, the super elevation to be provided is higher than what we have provided for 80 kilometers per hour. It means there is a difference between the value to be provided for 120 and which is being provided in actual for 80 kilometers per hour, and this difference is what is termed as Kant deficiency. Similarly, we take the another case where there is a train which is moving at a speed as at lower speed than 80 kilometers per hour, say 50 kilometers per hour is the speed. Now, for this 50 kilometers per hour, we require lesser amount of super elevation as compared to what we have provided with respect to 80 kilometers per hour. So, therefore, in this case, there is excess of the Kant which is already being provided, and the difference between the Kant provided and the Kant which could have been there for 50 kilometers per hour, This value is known as cant excess. So, these are the two conditions we have to consider while trying to find out the maximum permissible speed on a curve. So, in this case what we are doing in this particular case where we are taking the lower speed is that it is to be taken into consideration with cant axis. First of all, what we do is we calculate the value of the actual cant which is required based on the speed on which the goods trains are moving. Generally, the speed of the goods train is lower than the high speed trains in the passenger category. So, for that value of the goods train, the CA value is to be computed. So, this is going to be the lowest condition which is available. Now, from this one, then we add the cant excess, and as soon as we add the cant excess value which is allowed for that gauge of the track, we will be reaching the equilibrium condition. So, we are coming from the down towards the center point in this case, whereas in the previous case where we have talked about the higher speed, then we were coming down from the top to the middle condition, or we are going from middle to the top condition if we add the cant deficiency in the value of cant actually provided. So, now we are coming to the above condition, that is to a central equilibrium condition, and for this value of CA plus CE, where CE is the cant axis, we find out the maximum speed. So, we have this value of speed, we have the previous value of speed, and we have the maximum sanctioned speed already available. So, the speed corresponding to the length of the transition curve is another consideration, and based on the criteria how we provide a transition curve and how we design the transition curve, we have to look at that if there is any restriction imposed in the provision of the length of the transition curve, then the speed is to be computed. Otherwise, if there is no such restriction being imposed, whatever length comes can be provided in the field, then there is no requirement of using this criteria. So, this criteria generally gives the least value of the speed, and if the length of the transition curve cannot be increased, then the speed based on length of transition curve is also considered along with the above three methods. For high speed broad gauge tracks, one, the speed is restricted as a result of a rate of change of cant deficiency which is exceeding 55 mm per second. That is what is happening. It means to say this is the highest value of cant deficiency in the rate of change of cant deficiency which is being allowed, and if the value exceeds this one, that means we are going to a speed which is above the maximum safer permissible speed which could have been prescribed using this value. So, in that case we have to limit the cant deficiency to a lower value. In the terms of the mm, this value transforms into 100 mm. So, we have to go for a value lesser than 100 mm and then optimize and try to find out the restricted speed on that high speed track. So, these are some considerations which has to be made while computing the maximum permissible speed, because it has its safety implications. Now, we come to some of the technical words which have been used in the previous computations. One is cant. Cant is nothing but the same thing as super elevation, and that is how it is defined here. It is the difference in the height between the outer and inner rail on a curve, and this we have already seen that how this difference can be computed. Inner rail is maintained at its original level and is called the gradient rail, whereas cant deficiency is it occurs when the train runs at a speed higher than the equilibrium speed. So, as I have discussed previously too, that once that train is running at a speed higher than the equilibrium speed, then it means it requires a cant which is higher than the cant provided for the equilibrium speed, because E is directly proportional to the square of the speed, that is E is GV square divided by 127R. This is what we know. So, in this case, as it is going to be proportional to the square of the speed, it means higher value of cant is to be provided if the higher speed is available. So, in this case, if we are not doing this, then there is a deficiency in the cant being provided, and in this case it may result in overturning. So, that is a problem associated with the higher speeds being attained with respect to the equilibrium speed, and with respect to this criteria, this higher speed is to be restricted or is to be fixed. Similarly, there is another term which we have used, and that is Kent axis. And Kent axis can be defined, or it occurs when the trains are running at a speed lower than the equilibrium speed. And this is again we have discussed that if the speed is lower, then we require a lower amount of super elevation, again from the same concept that the super elevation is proportional to square of speed, and whereas what we have provided is higher than that one. Therefore, there is extra amount of super elevation already being provided. Now, when extra amount of super elevation is being provided, then it has a tendency to move the overall train or the rolling stock towards the inner side of the curve. Whereas, in the previous case, when we talk about the Kent deficiency, then because of the extra force which is being left, which is not being counteracted by super elevation, when the train is moving at a higher speed than the equilibrium speed, it will try to overturn it on the outer side of the curve. So, in this case, when it is coming in the Kent axis towards the inner side of the curve, there are all possibilities that derailment may take place. So, we have to control this derailment, or we have to control the overturning of the train in the two cases, that is Kent axis and Kent deficiency respectively. Now, we come to the limiting values. In this case, the limiting values are with respect to the speed which is lower than 100 kilometers per hour. So, we are taking the values for the broad gauge and the meter gauge. Here the maximum degree is 10 for broad gauge, it is 16 for meter gauge and 40 for narrow gauge. Then the minimum radius is 175 meters, again this already we have seen previously as broad gauge, 109 meters for meter gauge and 44 meters for a narrow gauge. So, in the case of narrow gauge we can have a sharper curve, whereas in the case of broad gauge sharper curve cannot be there. Maximum Kent is defined as a 165 mm in the case of A, B and C category of routes in broad gauge, and 140 mm as a D and E category of routes in broad gauge, where in the case of meter gauge it is 90 mm, and with the special permission we can go for 100 mm. Then for Kent deficiency, this maximum value of Kent deficiency is being restricted to 75 mm in the case of broad gauge and 50 mm in the case of meter gauge, and in special cases only for route A and B in the broad gauge category, this value of 75 mm can be upgraded to 100 mm. That is, we are interested in a higher speed movement in the case of route A and B only. Then in the case of Kent axis, the value is 75 mm for broad gauge and is 65 mm for meter gauge. The maximum Kent gradient, it is 1 in 720 in broad gauge and 1 in 720 in meter gauge. In exceptional cases, in the case of broad gauge only, not in the case of meter gauge or narrow gauge, it can be reduced to a value of 1 in 360, means it is made further steeper as compared to 1 in 720. Then rate of change of Kent. This rate of change of Kent in the case of here it is 35 mm per second. This is the desirable value, whereas at the maximum it can be attain a value of 55 mm per second. M is for maximum and D is for desirable as mentioned on this side, whereas in the case of the meter gauge the desirable and the maximum value remains the same, that is 35 mm per second. Then further, the values indicated in the previous slide for maximum Kent when speed is less than 100 kilometers per hour, whereas when the speeds are greater than this one, that is if we that is exceeding 120 kilometers per hour, then the maximum Kent is 165 mm up to 120 kilometers per hour. But when the speed is increased from 120 to 160, then it can be raised to 185 mm, and when it goes from 160 to 200 kilometers per hour, then it can be reached. Again it remains the same value as 185 mm. These are the different speed bands which have been defined and considered by the Indian Railways. And another way is that the maximum can at approximate condition can be computed as 1/10 to 1/12 of the gauge. So, whatever is the gauge value, if we take 1/10 or 1/12 of that one, then that is going to be the maximum Kent value. That is the rough way of computing or calculating the Kent. Then higher Kent deficiency means this is not CAN, this is CANT. Higher Kent deficiency means higher discomfort, higher unbalanced centrifugal force, and extra force and the lateral pressure on the outer rails. This I have already discussed as that if the speed is more than the equilibrium speed. So, we are left with the force which is not being eliminated, and the effect of this force is to take the vehicle towards the outer side, and when that is the lateral pressure on the outer rails is increasing, and due to this unbalanced condition of the centrifugal force, the discomfort will be there and there are chances of overturning. So, now we comes to the last condition where we have to calculate the value of Kent, and we have to calculate the value of the maximum speed permissible on any of the track. There are different steps which needs to be considered here. First of all, we have to calculate the Kent for the maximum sectional speed using the value GV square divided by 127 R, and this is designated here as Cm. Then this calculate the Kent for the slowest traffic, as we have seen in the case of the goods train. So, we have to calculate the Kent for that category also, that is what is Cs being defined here. Again the same formula is to be used. Then we add the Kent excess to it, that is Cs plus Ce. Then Ce value, as we have seen in the previous slide where we discussed about the permissible values of deficiency or excess. So, that value we can take and add to it. Then we calculate the Kent for the equilibrium speed, and that is designated as Cp. So, we have got three values here now as Cm, Cs plus Ce and Cp, and then these three values has to be just considered. Check for Kent deficiency Cd using Cm and Cn. Here we have this value of maximum value of the Kent which is provided for the maximum sanctional speed, and we have the Kent deficiency. If we just subtract Kent deficiency from the Cm value, we should achieve the equilibrium speed condition Kent, that is Cp, or here Cn is being defined in this way. If it is less than the standard value, then it is okay, but if it is not that, then the standard value is to be set. Further, the lowest or the above 3 is the permissible Kent Ca, and once we have got the permissible Kent Ca, then we add the Kent deficiency to this value, and we calculate the value of Vm, that is the maximum permissible speed, using the standard formula. The standard formula we have already seen previously. It is 0.27 multiplied with under root of the whole value as Ca plus Cd, and this is multiplied with R, and this value remains within the square root. So, now we come to one of the example. We are being given a 2 degree broad gauge track with the maximum sanctioned speed as 110 kilometers per hour. The equilibrium super elevation speed is 80 kilometers per hour, and the booked speed of goods train is 50 kilometers per hour. So, we have been given three values of the speeds, and the broad gauge is being designated by degrees. So, we have to compute the value of allowable maximum value of speed as well as the Kent. So, what we are doing here is that first of all we are computing the radius using this value of degrees. So, we are getting 875 meters. Then the super elevation for the equilibrium speed is computed, and this is with respect to the equilibrium super elevation speed of 80 kilometers per hour. So, this is being computed here in this form by GV square divided by 127 R formula, and we are getting 100.8 mm. Now, once we have got this value, then the super elevation for the maximum permissible speed is computed, which is given as 110 kilometers per hour, and for this value we are getting the value as 190.6 mm. So, what we are providing as an super elevation is 100.8 mm, whereas if we go to the maximum speed then it is 190.6 mm. This is what is the difference between these two is deficiency. So, the Kant deficiency is 190.6 minus 100.8 is 89.8 mm, that is the amount of Kant deficiency in this track, and this is less than the maximum Kant deficiency of 100 mm, hence the design is okay here. If it is going above 100 mm, then this is to be restricted to 100 mm. Then super elevation for the booked speed of the goods train is given, and for this value of 50 kilometers per hour we have to compute the value of super elevation, that comes out to be 39.4 mm. So, this is less than the actual condition. So, there is a excess of super elevation provided and we can check that also. So, this is 100.8 is the equilibrium Kant and this is minimum Kant. So, difference is 61.4 mm and this 61.4 mm is less than 75. So, hence it is allowed. So, the maximum speed potential will be 0.27 multiplied by this formula which we have seen. So, we get the value of 110.1 kilometers per hour. So, therefore, the maximum permissible speed will be the least of these following: the maximum sanctioned speed 110 kilometers per hour, the speed computed 110.1 kilometer per hour, and assuming that there is no restriction of the transition curve length, what we get is as 110 kilometers per hour. So, this is how we can compute the Kant as well as the maximum permissible speed on any track. So, we students, today in this lecture we have looked at the another aspect of geometric design, which is a very important aspect, that is speeds. And we have seen that the speed can be defined in different form. It may be the maximum permissible speed, the safe speed, the equilibrium speed, the average speed, and likewise. At the same time, when we are computing these values, we have to take care of the Kant deficiencies and Kant excess. Now, we will be continuing with some more things in the coming lectures related to the geometric design. We stop here at this point and I convey to you my thanks and goodbye.
Thank you.